So you have a continuous random variable. What is true about the probability that it's equal to some particular value? The probability x equals a. And what did people say? All right, at an overwhelming majority of 31 to 6, people have realized that it is 0 no matter what f is. And once again, this is because f tells you the height. If you were talking about x equals a, that is only one single point on the x-axis, and the area under one single point is 0. And in the same way the area of a line is 0, the area under one single point is 0. And so the probability for these continuous random variables is always an area, and that area is 0 under 1 point, no matter what f of a is. So it could be very, very tall, and the area would still be 0. To make it non-zero, you have to look at x is a little bit of an area around a. So like you'd say like x is between a and a plus 1. Then it would be something that is non-zero. Okay, that's very good. We're going to learn about a very special distribution. So not only some random variable x, but a very special one that is called the normal random variable. Normal, why is it called? Normal is a terrible name, but that's what it's called. It's so special, people call it the normal. Let's learn a little bit about the normal. Okay, I think you might have to open it and close it again to properly.
Yeah, it seems to be.
Now that you're connected to the HDMI, it should.
Yeah. Okay, let's just close that and tell it to. Let's just see if we can get that to open again.
It's not this button?
Huh?
It's not that button?
It is,
Okay.
Which is what I started with.
Okay. Yeah, now you're good.
Now we're good. Okay. So distribution we are about to discuss is, you probably know it as the most common model for a bell curve. Of course, you've heard of marks being belled and this kind of thing, but we all have a good sense of what a bell curve is. Professor Nika mentioned the idea of it being a bad name, calling it the normal distribution. Well, the question is, why was it called the normal distribution? And it really comes back to the time of early statisticians in the early 1900s were investigating the distribution of all kinds of particularly biological phenomena, not just biological, but particularly biological phenomena where they're measuring lots of things. They're measuring weights, they're measuring lengths, they're measuring, various bones and various body parts, etc. And they found that so many of these measurements had these approximate bell curves that it was kind of thought that a normal distribution, this bell-shaped distribution, was essentially normal in nature. And it was later on, as they studied more and more phenomena, that they found more and more exceptions to this idea of bell-shaped distributions, although there were still lots of bell-shaped distributions in nature. Now, the fact that there are lots of bell-shaped distributions in nature is not really why it is the most important distribution in statistics. We will discuss why it is the most important distribution in statistics as we move along. So the thing about this random variable is kind of, it's very funky. It is a continuous random variable, and it takes on some value between negative infinity and infinity, which gives a lot of possibilities. It definitely is a lot of possibilities.
Yeah, so the students are experts at this because of EV. It's just like EV can do infinite, is between 0 and infinity damage.
Okay.
The X random variable can be between minus infinity and infinity.
But EV is between 0 and infinity.
Well, okay, you have two EVs. I have my EV, you have your EV, and we subtract them. Now it's between minus infinity and infinity.
True enough.
Yeah.
True enough.
Okay, so
yes.
the students know.
Okay. It has two parameters, two numbers that characterize the distribution. We'll figure out what those mean in a moment. But the parameters are actually simply the things that we have calculated before, the mean, the expected value of x, and the standard deviation sigma, which is, of course, the square root of the variance. So these are kind of like very generic type parameters. So what we're going to do is we're going to draw it. And we're going to label the points of inflection at mu minus sigma and mu plus sigma. So what you want to do is learn how to draw a good normal distribution. We'll flip to a paper. And so here's the first thing I want you to do is draw a horizontal line with a little space under it. Oh, that's so good. You would have sworn I would used a ruler. And then what I want you to do is about the middle of that line there, draw a little dash, dash, dash down at perpendicular to that horizontal line. We got a dash, dash, dash. And then now we're going to draw the normal distribution. Now, you got to kind of like envision tobogganing on a hill, okay? We're going to start off on this hill, and we're going to start off kind of gently, and then the slope of the hill is going to get much steeper, so we're going to like speed up, and then the slope is going to level off, and we are going to come drifting, well, for a long time. Well, how long? Well, we'll discuss that in a moment. So here's what we're doing. I'm starting off kind of slow. Oh my goodness, my pen didn't do what I wanted it to do. It's a little cranky, but it's coming there, and then it's going to drift off, and I'm coming down this way, and then I start coasting, and I coast, and I coast, and I coast, and this is where it gets a little theoretical, because we know you can't really coast forever, but in fact, we do actually coast forever here. We're going to keep coasting there. Now, how far do I coast to? Well, this heads off to positive infinity. Okay. Now, let's just do the same thing on the other side. Try to keep it best you can to keep it symmetric. You know, there's the other side of the hill, and we'll go coasting down there. Wow, that was fun. Great fun. And again, on this side, we're going to head off to negative infinity. So what's kind of the cool part of this thing is that point where you go from accelerating to decelerating. Exactly what is that point? What do you label that point? That's the point of inflection, okay? And that turns out to be, well, where is this? So first of all, without actually doing any math on it, because this is a symmetric distribution around the center, in fact, it turns out that this is the mean of the distribution. And these points of inflection occur at mu plus sigma and mu minus sigma. So this is kind of cool. Okay, point of inflection. Let's label that. Let's use a nicer colored pen. And here's your other point of inflection. Okay, so this is quite cool because we can work with normal distributions of any mean, any standard deviation, and if the standard deviation is smaller, it'll pull up that way and the peak will get higher, or if the sigma gets larger, that thing's going to spread out more and the peak's going to come down. If we're keeping everything on the same scale, and we can vary the mean. So you can kind of think of how these distributions might move around. a little bit with different values of mu and sigma. We'll kind of reinforce that as we come along. But a key point about this whole thing is that the total area under the curve is 1, okay? So it is a, this is on this scale, we've got our x, and on this scale, this is our f of x. Okay, so f of x is simply the height of the curve at any particular value of x. So f of x is drawing the curve for us. Okay, so is that a famous curve? Well, let's just take a
Gary, do you know why it's really famous? There's a meme. We have to show the students the meme.
Oh, the meme.
In case they haven't seen the meme.
Okay.
There's the normal distribution in pop culture. Who's seen this meme before? A few people. This is a meme. There's supposed to be some people arguing. But the reason I like showing this is because they drew it wrong. So if you go and you look at the beautiful drawing that Professor Humphrey has done with the nice inflection points, this is the proper way to do it. These guys, they like drew it by hand or something, and it's all wrong. So every time you see this meme from now on, you will know they screwed up the normal distribution. They made it too pointy.
Yeah.
So it's very funny every time I see this. I laugh at the people. By the way, here is the graph on a computer. This is what it looks like, sort of exactly drawn according to spec, and you'll see that you can compare to the beautiful drawing over there and see that they are very lovely and very nice. I will say one nice thing on the computer is you can slide things around. So I made little sliders for mu. So if you slide mu around, you change the center of this thing. Maybe you want to make the center equal to 4. If you have some you know the average is 4, then your center would be 4. And then you can also change the sigma. The sigma is sort of the width of the distribution, right? So that it has points of inflection at mu plus sigma and mu minus sigma. So they're in there. So when I change sigma, it's going to get wider and more narrow. But actually, one other thing is going to happen in addition to getting wider and more narrow. So take your guess as to what you think will happen. Anyone want to share what they think will happen when I change the slider to make it wider or more narrow? In addition to getting wider and more narrow, one other thing is going to happen. Yeah. Yes, this is true. So the values like over here, when I make it wider, all these values will sort of get higher, right? Because right now they're very, very far away from the mean. And as I make it wider and wider, eventually this wave will sort of come over and make even the points at -4 bigger. But there is sort of one other visual effect. What would happen right at 4? What's going to happen? Yeah. Yeah, the height will increase or decrease. That's exactly right. So I think some people don't notice that. Let me make this automatically do it, because that's fun. So when you make it wider, you have to also make it shorter. And when you make it more narrow, it has to be taller. And that's because the area is always 1. So it cannot do one without the other. And so this is a thing that you should be aware of, is that it can be very spread out and very flat, or it can be very peaked in the middle in one spot. And the segment tells you the width and also the height in some sense.
Except you got to be a little careful when you're comparing two diagrams of normal distributions to make sure they're on the same scale of x.
Yeah.
Okay, because you can also mess around with the scale and take one that's really well spread out and move it up so the peak is, it looks higher, it really isn't higher in terms of f of x.
Yeah, very good. Yeah, there's a question over here. Sigma. Yeah. Yes, so it turns out I wrote out the formula. We're never going to actually use the formula. So you don't need to know the formula. You just need to know properties of it. But it turns out the height has a factor of 1 over square root of 2 pi sigma squared. Who put pi there? So the height depends on sigma. And then also there's a sigma in the function over here. So if you know how functions scale, this is a width scaling of sigma, and this one is a height scaling of sigma. And they're both there. I'm not sure if that answers your question. Does that?
We're going to come back to that question.
We're going to come back.
We're going to come
Did I
back.
spoil the 2 pi? Was that
It's
a
okay.
surprise?
It's okay. But we're gonna have to say a little bit more about that.
All right.
Okay. So back to our slides. Okay, normal distribution is also called the Gaussian distribution after the mathematician Carl Friedrich Gauss. Great German mathematician. Actually, I'm going to ask you to say a little bit more about
Gauss.
Gauss, but
Gauss
not
was
yet.
everyone calls him the Prince of Mathematics. I don't know why they call him that, but that is
That's because him and Euler kind of have to compete for who
who's
is
the best.
king, right?
I will tell you a funny story about the name of this distribution. I made a video once where it was all about this distribution, but I don't call it the Gaussian distribution. I call it the Gaussian distribution because I'm lazy and I smoosh my vowels. And then people in the comments made fun of me. But then there's a famous internet guy who does pronunciations. His name is Jeff Lindsay, and he makes these like really great videos about how different people pronounce different things. And I emailed him, and he emailed back, and he says, some people say it like that. So it's okay. Apparently it's the same as like Parisian versus
Parisian.
To me, you sound like very like stuck-up British if you say, oh, Parisian. But it should be Parisian, so Gaussian, right? That's like the street way to say Gaussian. Gaussian, yes. Okay, difference of opinion.
Of course, we didn't typically call it normal.
If I recall correctly in the email, he said maybe younger people are calling it Gaussian instead of Gaussian. So maybe your way is dying out, Gary.
Oh, it could be.
It could be.
Just kind of like me, it's like the way it is.
All right.
Okay.
So say it however you want.
Okay. So, famous mathematician, and for the anniversary, they put out a coin. Beautiful coin. And notice, 20 mark, silver coin. Sells for a little over $100. You have to buy one.
What's a mark?
Unit of currency for Germany prior to the introduction of the euro.
Before the euro, they had
Before
marks.
the euro. So a couple things to notice on there is that they put the distribution, the normal distribution up, or Gaussian distribution. And again, you see it's centered about mu, and the y is just the scale that for f of x, the same difference there. And you notice they mark the points of inflection at mu minus sigma and mu plus sigma. They've got the x there. Then they've got this other curve floating through here. Anybody want to take a guess what that curve is that they've got floating through there? And it's not to the same scale as the other. Anybody want to take a guess what that's? What do you think? Yes, it is the cumulative distribution they're putting in there on a different scale. So they also produced a 10-mark note, and got to mention this 10-mark note. These are available fairly inexpensively. You probably need to get one of these in your life sometime because they're just like so cool. And in fact, I got really lucky because I bought one. It turned out it had my initials on it. So I thought, holy cow, like this is like, how could I? But hey, let's take a look up to the left of Gauss's head here. And Professor Nika has already teased this thing here. Take a look there. It has got a graph of the PDF. Look at there's our normal curve. It's a little grainy.
Why does it matter if it's a PDF or a JPEG or whatever? What's the?
Oh, I was trying to. This is so confusing. The PDF file format and the probability density function.
PDF stands for probability density function. Yeah. What a good acronym. We should take it away from Adobe.
So it's a little foggy up there. Not much better on the screen there, wouldn't you say?
It's very nice.
So let's go back to that one a little bit here. But the thing is, now you got it in real nice, crisp fashion. Can you just bring that one up again?
Yeah. Here's the formula in Desmos. Written out like this.
Okay, so I got to point out here that it's got a pi, it's got an e, and it's got a root of 2 on it.
Oh, yeah?
Now, Are those not the three most famous irrational numbers? You got any more famous than that?
No, those are the only three I know. Yeah.
I don't believe that, but nonetheless.
Well, it's hard to come up with a rational. Okay, all the other square roots, square root of 3, square root of 5.
Exactly, but root 2 is like...
Root 2 is the best one.
It's
the
the
OG,
best one.
the first guy.
So is it not absolutely weird that the three most famous irrational numbers are in the one equation?
You could even argue that this -1 in the exponent is actually I squared. You
could argue that.
So
right.
you maybe sort of.
But I mean, all those things coming together. I mean, does that not show you something that there's something weird in the mysteries of the universe?
There's a question over here. Yeah. Ah, yes. Okay. EXP means e to the power of. It's the exponential base e. So on the dollar bill or the mark bill, they said e to the power of. Wow, that is very blurry on the screen. But on my screen, it is x, and x is e to the power of. Yeah.
It's a good question. Good
yeah,
question.
Fantastic.
Okay. So where are we heading next? Well, where are we heading next? Back to this. Okay. Dum-dum-dum. Okay. I'll be posting these slides. I didn't think you needed these ones beforehand. No point of writing this out. But just kind of an example of fitting a normal distribution in real life. These were chest measurements of Scottish soldiers taken way back in the 1700s, early 1800s. Okay, and they were published in the Edinburgh Medical and Surgical Journal of 1817. And consisting of over 5,000 Scottish soldiers. And the data set looks like this. And so these are the midpoints. So 33 would be like 32.5 to 33.5 inches. 34 is the midpoint of 33.5 to 34.5 inches that have a decision rule for anything kind of exact, etc. So they've been categorized, rounded off to the nearest inch. And if we plot those things, as a histogram, we would have these discrete bins here. But then if we fit a normal distribution over that with the same mean and standard deviation, that is the curve in the color here. And the idea being that we're using a normal distribution, the normal distribution to model a real phenomena, okay, which is the chest circumference. So I think you can see the idea that the bell-shaped distribution of the chest measurements, they can be pretty well approximated by this theoretical model. Okay, so it's important to recognize, again, we're trying to emphasize is that the density function f of x gives the height of the curve for a value x, but it doesn't calculate p of x directly. And how we get a probability is we have to get a probability between two values on the x-axis. And the probability is going to be the area between A and B under the curve there. Now, since x is continuous, just this is to kind of emphasize that whether we say A is less than x or A is less than or equal to x is irrelevant. Whether we say x is less than b or x is less than or equal to b is irrelevant. So these are all equivalent expressions. We often mix them up. Sometimes we'll say, what's the probability A is less than or x is less than 1.2, and sometimes we'll say what's the probability x is less than or equal to 1.2, and that's just to get you to say, the less than or equal to doesn't matter in this case. So how are we going to get those probabilities? Well, for something, some of our curves, we worked out things like triangles and rectangles geometrically. And once you get into integration, there will be lots of density functions that you could get the the area under the curve very nicely using integration. But the normal curve is not one that integrates nicely. Instead, we are going to use a table to do it. And hence, we are going to pass out tables now. Would you like to pass out some tables on that side? We'll get some tables going on this side. And let's see, we'll start some halfway here and the other halfway further back. Let's just see, how are we doing here? Let's get some back about here. So those are getting passed around, just a couple extra points.
Gary, I noticed on your slide you said it doesn't integrate nicely. Can I make a comment about that?
Yes.
Well, so first of all, you might know from calculus class that this whole thing we've been talking about, area under the curve, actually goes by this big symbol with the integral sign. You might have seen that before. And you might have seen in calculus class, sometimes you have a nasty function that, quote, doesn't integrate nicely, like 1 over x squared plus 1. This is a real nasty bugger. 1 over x squared plus 1. If you try to do this one and you don't know the tricks, it will take you a long time. But you can eventually do it. By the way, if you've never seen this, don't be scared. You don't need to know it for this course. We're sort of making a little side comment here. This is, does anyone know what this one is? Yeah. It is arctan. This one is arctan. See, if you get really good at integration, you learn some of these things. Don't forget the plus c or you lose marks. So sometimes they look nasty. And I would say this one does not integrate nicely, but you can eventually integrate it. The one we want to do in this course, the normal distribution, that would be an integral like this of e to the minus x squared. Let's just forget about the rest. Let's put it over 2. Okay. And this one, not only does it not integrate nicely in that maybe there's an answer, but it's a lot of work to get to, but this one has no antiderivative. So this operation of trying to find a formula for this area is doomed to fail. And when I say it has no, I mean in terms of exponential functions, in terms of ordinary functions. So this is like the first example. I'll say ordinary functions. So you can't write down the answer in terms of like some simpler functions like arctan or something. This is really kind of the first example of if somebody asks you to integrate this in calculus class, there's no way to do it. it has been proven that it's impossible to find an answer to this integral in terms of the ordinary functions. So I think it's quite generous to say it doesn't integrate nicely. I would say it does not integrate using the ordinary functions from mathematics. You can define what the integral is. And in fact, going back to the computer quickly, I think Desmos has this. The people have given a name exp to this exponential function. That's an ordinary function. But this area function for something like the area of a piece of this curve, let's make it a little bit pointier and zoom in a bit. Okay, so I can slide the area around here to get this like purple area. And these purple areas will be given by something called the error function, which is called erf of a. We'll give you the error function. I guess I have to subtract mu. Let's make mu 0, 1, and 0 here. 0 and 1. And then the area really will be this erf. So that area in purple right now is 0.999. If I slide it back to here, it'll be, oh, okay, I gotta add a half or something. Well, sort of the integral of this guy is a new function that has no nice formula, and they named him erf. The name of the function is erf. I think erf stands for error function, but I think it's very funny to think of my little pet dog erf. Maybe I'll name my next pet erf. Okay, I'm gonna stop talking now. Let's go back to the regularly scheduled programming.
So, following up on that, we define something called a standard normal distribution. A standard normal distribution is just a normal distribution that has a mean of 0 and a standard deviation of 1. There's actually something a little interesting about the mean being 0 there. Many people find it, or they get fooled on a test on this one. So you're here at class, so you would never get fooled on this one. Is not to realize that the mean, in fact, can be negative. Okay, and we can think about things like a distribution of temperatures over in January in the Yukon or something like that. Yes, having a mean temperature that's negative is nothing wrong with that at all. Okay, so we often use this. In fact, very, very often we will use a Z to represent a standard normal random variable. So what's been handed out to you is a set of tables, and these come from Dr. Jeremy Balka. He teaches Stat 2040. Some of you are taking it right now. Some of you will take it in the future. He has produced these tables, and we will learn how to work with these tables. And what they're going to do is they give cumulative probabilities, the probability that the random variable z is less than or equal to some particular value of z for various values of z, for various values of little z. So let's do a few values here. Let's do a few values. And let's start off with the probability z is less than 1.25. Okay, and I just need the dot camera here. Want the probability z is less than 1.25. So notice your table has two sides to it. Okay, and which side you'd like to call the first and the second, but it starts really on this side, where you're starting at the negative infinity end, and they start increasing the value of z as you go from left to right. And what you've got here, you notice those, well, they kind of work backwards here on this one, because it kind of starts from, it's starting at the far end and coming in, and then these two values here are kind of like oddballs.
Here, just off the page there, Gary.
Yeah, those are oddballs. Crappy pen. These are way out values. We'll get to those way out values. So what it is this is to one decimal place, and then you go across for a second decimal place. And let's just start with our example. We'll flip the other side where the values of z are positive, and then I want the cumulative probability for 1.25. So I identify it's going to be in that row right there, 1.2, and then second decimal place is going to be 5. So 1.205, and then I will circle that value, 0.8944. So the very first one we've worked out is the probability x is less than 1.25. Where will I write that? Probability, z is less than 1.25 equals 0.8944. Okay, so does everybody see that? This is one that you don't want to be saying, I'm going to check it later on. Just check with your friends or something like this, your colleagues around here. Just make sure everybody understands. Everybody know where that value came from. You got that right on your own sheet, right? Okay, let's go to the next one here. The probability z is less than negative 1.25. Oh, negative 1.25. Okay.
I do have a helpful comment.
Yes.
Why is it so important to be able to use these tables when we can look it up on the internet these days?
Because on the test, you're not
Oh,
going to get to look it up on the internet.
test, you'll be given one of these tables, and it'll say, please find the probability z is less than 1.25, or
Yes.
use that as part of a question.
Yes.
And you need to be able to do it. You know, in the midterm we just gave you, there were some little dopey tables that had 4 entries. You should think of this as like a table that'll be on the final that'll have 100 entries, and you need to be able to know how to use it, or you won't be able to answer those questions.
Mm-hmm.
What did you get, by the way? You got 0.894 before?
0.8944 was probability z is less than 1.25.
Okay,
Okay, I'm going to draw that one out in a moment, but I'm going to come back to this after I do the next one. I want to do the next one first. Negative 1.25, negative 1.25, there's the negative 1.2, and there is the 5 right there. So I came up with the probability z is less than negative 1.25 equals 0.1056. Okay, let's just sketch those out a little bit. So everybody good with that one? Less than negative 1.25, we're good on that? Okay, let's just take a look at what we did. So I'll tell you, if you draw pictures, when you're solving these problems, you will make, on average, many fewer mistakes if you actually draw the picture of what you want, okay? And it's very common for people to go the wrong way and this kind of thing. So let me just draw the picture. So our very first one, you get kind of into drawing your normal curves, okay? You don't have to be perfect about it. So this is the distribution of z. Okay, this is the standard normal, so that the mean is 0. And remember, again, the points of inflection were at plus and minus 1 standard deviation, but the standard deviation is at 1. So, you know, if I wanted to draw a little bit more there, I could put those at negative 1 and 1. But the first one I got asked is, what's the probability z is less than 1.25? And 1.25, 1.25 is going to be up here, about right here, okay? So there's the 1.25. And the first question I wanted to know was, what was the probability z is less than 1.25? I want to know what is the area under the curve below the x of 1.25, or the z of 1.25. So what I want to know is, what is all this area here? Nicely shaded in, and we said to ourselves that is this area here. Shaded was the probability z is less than 1.25 equals 0. Well, I know what it is, 0.8944. And then the second question, I'm drawing a second picture because ink's rather cheap.
Yeah, you're just off the bottom there again, Gary.
I'm off the bottom. Yeah, well, okay. Didn't get it lined up quite the way I wanted. Kind of wanted to have a up and down, but it's okay. Okay, so there's my 1. There's my negative 1. And this time I wanted less than negative 1.25. And so negative 1.25 was right there, 1.25. And so I wanted this area. And so this area here was the probability z is less than negative 1.25 equals 0.1056. Now, what you may have noticed here is, again, remember the distribution is symmetrical. So this area here, 0.1056, note the probability that z is less than negative 1.25 equals the probability that z is greater than 1.25, which is 1 minus the probability z is less than negative 1.25. Other words, it was 1 minus 0.8944 equals 0.1056. So there's kind of like extra detail in there. I mean, but really the point we're trying to make here is that because of the symmetry about the mean, you can use this for getting, we'll use this for getting probabilities in different ways, but you kind of get used to flipping back and forth and saying, will I get the, if I need to get an upper tail probability, well, that's going to be 1 minus the so-called lower tail probability. So let's see what other questions we can get. Probability z is greater than or equal to 2.43.
You have them do it if you.
Do we need to look that one up? I'm not gonna show them where I get this off the table, but we're just going to say for the third one here, the probability z, I said greater than or equal to 2.43. Again, don't let the equality throw you. It just doesn't matter. Okay, so I got two solutions here. I'm going to give you two solutions. One is to do 1 minus the probability that z is less than 2.43. Okay, 2.43. Let's get that little sucker. 2.43, 0.9925. 1 minus 0.9925 equals 0.0075. Or the probability z is greater than or equal to 2.43 equals the probability that z is less than negative 2.43. Whether you want to put an equal or not doesn't make any difference. So then I could just go directly to my table, negative 2.43, and there it is, 0.0075, right? So it's really, this is an easy solution. This is an even easier solution if you could just make that flip in your head there.
So in other words, the flip is justified because the distribution is symmetric.
Symmetric about 0 because it's a standard normal distribution. This is a key thing here is that this one is symmetric about 0. Okay, let's just try. Okay, so a little.
Oh, you're on the here.
Okay.
Let me put you back up.
Okay, so this one here, very common type question is let's get the probability that z is between negative 1 and 1. Okay, so if we're drawing that picture, that's kind of.
Yeah, just below.
Am I off the screen again? Okay, yep. Thanks. There. And again, remember these were at the points of inflection. So there's your negative 1, there's your 1. And so I want this area in the center. So I want to get this area in the center.
Hey, wait a second,
here.
That's not in the table. The table only does, if you look at the little picture, the table only does the gray areas all the way to the left. How are we going to get this?
Oh, well.
That's not in the table. I don't think we can do it.
I don't believe you. You're lying. He's lying. He knows how to do it.
I'm just sleepy. Maybe I'm sleepy.
Oh, maybe you're sleepy. That can happen. Okay. So we got multiple ways to attack this. Okay. Let's just kind of think of some of the ways we could attack this. Okay. Well, we'll go with a couple of ways. Well, maybe we'll go with more than a couple of ways. Well, let's go with one. Well, one of the things you could do is take the probability that z is less than 1 and subtract the probability that z is less than negative 1. Who likes that way? I don't dislike it.
I can't do this way unless we draw a picture. We have to shade in. What do these look like?
Okay. Well, Z is less than 1 is everything below 1.
Oh, okay.
And then, but I don't want this piece, so I will subtract the Z is less than negative 1.
So Z is less than 1 is the red area, plus this little dopey tail over here. And then we subtract off the little dopey tail.
Yes.
Oh, nice.
Yes, nice. Okay, so let's do this one. And so this is going to be 0.8413 minus. Table is my friend. 0.1587. And what do we get there? 0.68. 0.68. Did I get that right?
4 something? 3.
Pardon?
6835?
Pardon?
Yeah, I got 6835, but I did it quickly and I'm sleepy, so I don't know if it's right.
It can't be 3.5. It can't be. Anybody want to tell me what that?
3.6?
Huh?
3.6? 2.6. 2.6. 2.6. Look, it was my
6.826.
my fourth guess. I got it.
Okay. Or let's do another solution. One other way is to recognize again that we've got the symmetry of the tails. What if we did 1 minus 2 times the probability that Z is less than negative 1?
No, now this is truly crazy. You just multiply by 2? What? Where did that come from?
Because the area less than negative 1 is the same as the area greater than 1. So if I just get those 2 tails, then all I have to do is get one of them, and then I can double that. And then I've got the area of the 2 tails, subtract that from 1. Oh, that looks like a nice way to go about it. So let's go 1 minus 2 times 0.1587. And so what have we got? 1 minus. What have we got there?
I did it all. It works out to 0.6826. Nailed
0.
it. I used the result.
Oh, you just did it all. Well, you are very fancy.
I think the adjective that applies today is sleeping.
So what did that multiply out to? 0.3.
3164.
316.
74. Oh.
74.
Oh. Now I'm embarrassed.
Okay, so that's it for today. Next day we do some things with other means and variances. Monday's lecture will likely not be recorded, so I want to just point that out. So you want to be here on Monday.
Yes, I will be gone on Monday.
I will point
Professor
out
Humphrey will do it
that 68%, that approximate 68% is an important number. And we'll delve into that a little bit more as we move along.